Hello everyone, my name is Marius Hadry and I am going to present a vision paper of the ICPE 2022 with the title Fate Towards Flexible and Adaptive Distance Estimation Considering Obstacles. I conducted this work together with my colleagues Veronika Lesch and Samuel Kunev. All three of us are from the University of Würzburg in Germany. First of all, I'd like to present you some numbers about the transportation usage in Germany in the year 2020. The figure shows the amount of billion ton kilometers transported by the respective mean of transportation. We can easily see that mostly trucks are used within Germany. Due to the high transportation volume, the logistic industry is permanently searching for ways to improve their workflows. For instance, the facility location problem tackles the issue of placing depots in spots that minimize the operational costs. However, in order to determine the cost, the distance between the place facility and customers has to be calculated. This is usually done using the line distance when applying optimization algorithms because it is an easy and fast way for the estimation. The downside of using the simple line distance is that it does not consider obstacles. This is especially a drawback in a scenario where customers and the depot are separated by, for example, a river, where one needs to take a route that includes a bridge. While street networks could be used for achieving accurate distance measures that account for all kinds of obstacles, they are usually too slow in the context of optimization algorithms where many distance calculations are required. Thus, in the literature, the line distance is still used for the facility location problem, but there are also other functions that are applied, like the Manhattan distance. Furthermore, visibility graphs could be applied, but the insertion of nodes is expensive, which is infeasible for optimization algorithms that move facilities often. So, fate aims to be a trade off between the accurate but slow street graphs and inaccurate but fast mathematical functions. Furthermore, it should not rely on node insertions for the distance estimation like it is the case for the visibility graphs. In summary, fate aims to be a trade off between accuracy and efficiency by using a simplified graph. Here, we can see a schematic illustration of the approach. On a higher level, the approach can be divided into a pre-processing phase and an estimation phase. During the pre-processing phase, an abstract map is created from a detailed map. Then, a grid is used to divide the abstract map into fields, and for each field, the passability is determined. Based on the passability property, a passability graph is built, which is then used for the distance estimation. The pre-processing phase has to be conducted only once for the region under observation, and multiple distance estimations can be calculated with that graph. It is important to note that the grid is only static at this point and not adaptive, but more on that issue later. The previously presented scheme was implemented as a prototype in Python and shortly evaluated. For the evaluation, we considered an area of approximately 6,100 square kilometers around Würzburg. While the routable street graph obtained from OpenStreetMaps data consisted of 190,000 nodes, our simplified graph only contained roughly 60,000 nodes, which is a node reduction of 70%. We then compared our method to other distance functions, namely the Haversine function, which is the line distance on a sphere, and the Manhattan distance function. Furthermore, we used PG routing to calculate routes on the OpenStreetMaps data. For the evaluation, a source and target point were selected, and each method was used 30 times for the distance calculation. The results are reported in the following table. In terms of the distance, we can see that the prototype of fate is better than the Haversine function, but worse than the other methods. For the selected source and target node, the Manhattan distance worked quite well due to the rather short distance and both points being in or close to the city. We also measured the time it took to identify the source and target node for the routing process. While it took 200 milliseconds on average to determine the starting point via SQL in the routable database, Fate achieved the node identification in less than a millisecond. The mathematical functions do not rely on graphs and thus do not have a procedure for node identification. For the distance calculations, both mathematical functions required less than 1 millisecond of time. Routing on the street network required 500 milliseconds on average, while Fate only required roughly 2 milliseconds. This shows that Fate is much faster and a trade-off between accuracy and efficiency was achieved. Next, I'd like to present the outlook for Fate. The current prototype does only apply a static grid, which is not changed after an initial pre-processing phase. However, fields could be merged and hence the grid size adapted to further reduce the number of nodes. One way to achieve this would be to take information about the population in an area and merge fields in areas where only few people live. Furthermore, we could add gradations between passable nodes and obstacles. This would allow to adapt the edge weights between nodes to further improve the accuracy. For instance, fields that contain serpentines could have a negative impact on connected edge weights. Lastly, we could also incorporate user goals into the approach. This would allow the user to specify the need of accuracy and efficiency, and the passability graph could be adapted accordingly. One way to achieve such adaptive behavior could be the application of the LRAM loop in a new phase between the preprocessing and distance estimation phase. Here, the users could enter their goals and the passability graph could be adapted based on representative routes. Now that I presented the idea and the first evaluation results of the prototype, I want to dive a little deeper into the workings of it. The pre-processing phase starts with retrieving map data. We use data from OpenStreetMaps, which can be seen in this screenshot. The most relevant part for us are the river and bridges for cars. The next step is about the creation of the abstract map. As we do not want to use the street network for our estimation technique, we filtered the data from OpenStreetMaps using QGIS, a free and open source geographic information system. As we can see, only the river and bridges are left after the filtering process, and the data was then exported as an image file. Now that we have the image file containing only relevant information, we divide it into grid fields. While the size of the grid fields is static for the prototype, we aim to vary the size based on different factors as previously explained. For the prototype, each grid field has a corresponding height of 440 meters and a width of about 230 meters. Next, we analyze the content of each grid field and define the passability of each field. We will color fields containing obstacles black and passable fields white. So, fields with bridges will remain white, while fields containing water will be colored black. This is the resulting grid representing the passability property of each field. The passability property of each grid field is the base for the creation of the passability graph. Next, each field is converted to a node and their color is assigned based on the passability property. Now we have to determine the connections between the nodes. Edges are inserted between adjacent white nodes only. Thus, black nodes do not have edges assigned. Here we can see a short example of the inserted edges. Each edge has a weight corresponding to the direction it takes. So, we can account for diagonal edges and are also able to consider grid fields that are not the same in height and width. The final step is to use the created graph for distance estimation. Here we can already see two locations placed on the grid. Now, one way would be to simply apply the great circle distance, but we can see that this line would cross the river at a position without a bridge. So, we apply the Dijkstra algorithm to our passability graph and receive the shortest distance considering a bridge. To get the final distance estimation, the edge weights on the way from source to target have to be summed up. So, to summarize this presentation, we have seen a motivating example, namely the facility location problem, where usually many distance calculations are required during the application of optimization algorithms. To tackle this problem, FATE was proposed, which can be divided into a pre-processing and estimation phase. We have already seen the first evaluation results of the prototype, which seem promising. However, there are still concepts we want to integrate into the approach, and after this integration, we want to conduct an extensive evaluation to verify fate. I thank you very much for watching this presentation, and I'm looking forward for your questions.